My name is Hadi Jahanshahi. I am presenting the paper predicting the number of reported bugs in a software repository. It's my honor to present on behalf of my co-authors and supervisors, Dr. Cevik and Dr. Ayse Basar. This is the outline of the presentation. In the beginning, we will have an introduction to the problem, its importance, and the way we deal with it. Then our contribution considering previous works will be discussed. Afterwards, the research questions will be defined, and then I will talk about the methodology, data preprocessing, and performance metrics. Finally, I present the result and concluding remarks. Why is predicting the number of bugs reported to a system important? Advanced knowledge of the likely number of bugs which is discovered in a software system helps developers in designating sufficient resources at convenient time. The developers may also use such information to take necessary action to increase the quality of the system and in turn, customer satisfaction. Bug prediction is a crucial task in software engineering. It lends insight for practitioners to prepare their resources before their system becomes overwhelmed with defects. Most of the previous studies looked at bug prediction as a classification problem. We have three types of the problem. One of them is bug prediction. The second one is predicting the number of bugs. And the last one that we focus in this paper is predicting the number of reported bugs. Some study look at the problem as a binary classification, where a software entity is classified either as buggy or non-buggy or clean. This is the classification task. This classification task mainly uses code metrics as the attribute while fitting the model and predicting the bug in the software, whether a part of a code is buggy or not. In the same way, predicting the number of bugs uses similar features to fit a regression model on the dataset. Therefore, we can say that they have the same roots, those first options. But one of them is predicting the number of bugs, the other, you look at the problem as a binary problem. On the other hand, we can also predict the number of reported bugs in a software repository. That is, the number of bugs users of a product are reporting using bug tracking systems. The main concern of the paper I'm presenting is fulfilling the latter task. In this paper, using Python code, we have mined the number of reported bugs to the Mozilla bug repository called Bugzilla from January 2010 to December 2019. The data are split to the weekly bug number, and there exist 522 weeks in total. As an exogenous factor, we extracted the release times of Mozilla updates to see whether multivariate modeling can enhance the performance of the prediction models. We also use different time series prediction methods to predict the number of reported bugs to Mozilla Firefox. And then we compare and contrast their performance. Previous studies mostly use generic time series models. For example, auto-regressive integrated moving average or ARIMA model, which is a famous one. Exponential smoothing that we have also used in this paper, polynomial regression, and some other approaches. In most cases, they compare different algorithms with each other without having a concrete baseline. To alleviate this problem or this issue, we defined lag prediction as a naive baseline. So one of the contributions of the paper is defining the baseline. And the baseline is predicted value for the target step is exactly equal to the last observed value. It means what we will have at time t plus 1 is equal to what we have already at time t. There are also some other study. They use time series analysis to determine seasonality and trends. That's another study that we have also covered in the paper. And they consider the evolution of human aspects in software engineering. But what we do here is a little bit different. We just focus on the number of reported bugs in a software as a metric, which helps developer maintain the quality of the software. Wang and Zhang use a different approach to predict defect numbers. They designed defect state transition models and applied the Markovian method to predict the number of defects at each state in the future. Other studies also consider different software levels for their defect number prediction. Our work differs from them as we consider the bug reported to the system, regardless of whether it is valid or not, rather than the number of bugs existing in software for different granularity like method level or file level of the system. These are our research questions. We defined two different research questions. First, how accurately the number of bugs in a project can be predicted using time series analysis. Time series prediction assumes that there are some patterns in the time series, making it feasible for prediction. Nonetheless, it's not always the case, so we will investigate the accuracy of the proposed models. The second research question is, how feasible is long-term bug number prediction? Not all models are able to predict more than one step ahead. Therefore, we investigate the feasibility and sensitivity of different models to long-term prediction. Before applying time series models, we first check certain requirements to ensure that the data is stationary because it's important for time series prediction. We conduct augmented Dickey-Fuller or ADF method. This ADF test determines the number of lags by the archaic information criterion or AIC. The null hypothesis is that the data are non-stationary, but the p-value of the test that we had was 0.012, thus we reject the null hypothesis. Therefore, the data can be modeled directly and there is no need to have supplementary pre-processing or transformation. To further investigate the result of the test, we conduct autocorrelation function and partial autocorrelation function. We call them as ACF or PACF. ACF defines how well the current value of the series is related to its past values, whereas PACF shows the correlation of the residuals with the next lag value. The sharp cutoff in PACF represents the number of auto-regressive or AR terms, P in our model, while a sharp drop in ACF is associated with moving average terms, like what we call it as Q in the model that we have. Here, as you see in the graph of the PACF, we have a sharp drop here when the lag is 2. Here, it's almost 2. Indicating the number of AR terms, P is 2. And for ACF, we do not have such a pattern. So we assume that Q is equal to 0 because we don't have any sharp drop as we have in PACF. In order to train time series models on the data, we have applied rolling method. The idea is that we train the dataset from time 0 to t, from here 0 to t, and then we test the model on the time t plus 1. In the next step, we add that test to the training set. So our training set will include everything from time 0 to time t plus 1. And then the testing part would be applied on time t plus 2. So it is how it works and it will continue to the end. We call it as rolling approach. We have extracted the number of reported bugs from the Mozilla bug repository. The bug-related information for Mozilla and its products is tracked in Bugzilla system. So there is another website. You can see the address here, bugzilla.mozilla.org. We gathered the number of reported bugs for Mozilla during the past decade. The total number of bugs is 1,450. Here, this figure, in the paper it is figure 2. Figure 2 demonstrates the arrival and resolved bugs in the Mozilla project. As it can be seen in the figure, Mozilla Suite weekly bug arrival range between something almost 50 to 558, which is the maximum one here. The clear outlier is also shown by a circle, but this red circle here, we remove that one because it might affect our prediction. Let's talk about the forecasting models. We consider different algorithms plus a baseline. Algorithms that we are considering here is LSTM, ARIMA, exponential smoothing, weighted moving average, and random forest regressor. We also defined exogenous variables to examine the effect of external and seasonal variables on the prediction performance. The exogenous variables include branch dates, week of the month of the year, and the year of the bug report. Here, the naive baseline assumes the number of bugs at time t is equal to that of time t minus 1. That's what we defined before. EXP, which stands for exponential smoothing, consider two factors in its prediction: the forecast value at previous timestamp and its actual value. Therefore, it is defined as the formula that you can see here. XT is defined based on what we have at time t minus 1, our prediction, and also the real value at time t minus 1. And weighted moving average simply forecast based on the weighted average of the previous steps. ARIMA is the most popular models used for time series prediction. You can see the generic form of ARIMA here. This is the generic form of ARIMA model. Alpha I and beta j represent the linear coefficient of the model. ET minus j here is the error concerning the mean, and D, which is defined here, is the degree of non-stationary homogeneity that we had. P and Q also are defined using AC function and PAC function that we saw in the previous slides. The next one is random forest. We applied random forest regressor. Random forest is less prone to overfitting in the data. We applied random forest regressor as a new method that has not been used in this domain. The last one is LSTM. We use the LSTM structure defined by Hochreiter and Schmidt-Huber as follows. This is the formula of LSTM model. Here, B in all of the equation, B, F, B, I, B, C, and B, O are the bias term. FT here is the forget gate. This is forget gate, deciding which information coming from hidden state at HT minus 1 and the new input, which is XT, should be discarded and should be removed from the prediction. Update layer, here IT selects critical information to be stored and multiplied with candidate vector C hat T. So the output of multiplication of this IT C hat T plus what we have from FT, or the forget gate, multiplied with C T minus 1, C from the previous time, will include the C vector as the output. The model decides which information should be reported, and the reported output is defined by OT, which is the output of the model. Also here you can see the model parameters. Also they are shown in the paper as well. For instance, the number of previous steps that we are considering in weighted moving average is 2, and the weight of the previous step is 66, but T minus 2, which is 2 steps before, is 33%. After designing the experiment, we have to define some performance metrics. Here we use RMSE, or root mean square error, R squared, the second one, error percentage, which is the percentage of the error in the output that we have predicted, and also median absolute error, or MAE, and a standard error deviation, STD in our case. Table 2 shows the performance of each method. We had EXP, WMA, ARIMA, and ARIMA X and LSTM X means that they are using also exogenous variables. ARIMA by itself doesn't use any exogenous variable, but when we add X to the name of any method here, it means that we are also including exogenous variable. Table 2 shows the performance of each method. Random forest with exogenous variable, or RFX, has the best performance in terms of RMSE. Also, it's bold-faced to make it easier to see. RMSE, error percentage, and also standard error has the best value for all of them. But surprisingly, the simple exponential smoothing, which is a very simple primitive approach, generates reliable prediction in terms of MAE, or median absolute error, and R squared. That's something nice to also consider here. We observe that adding exogenous variable does not necessarily augment the performance of the algorithms, including ARIMA-X and LSTM-X. But for RFX, it's completely different. It outperforms normal random forest. One of the reasons could be the sensitivity of those algorithms to new features. Random forest can deal with new features that might be unimportant or have a negligible effect on the output. Therefore, RFX has a better performance than a simple random forest regressor. The second part is for long-term prediction. As for long prediction, the error of the model is accumulated. The future predictions would not be as accurate as the closer ones. This is what we expect to see. Here, we analyze the performance of the models for a 3 months bug number prediction. So as you see, the number of weeks is 12 here. It means that it is for 3 months bug number prediction. Figure 6 shows that LSTM with the capability of having both long and short-term memory, because we have for-good gate, as we have discussed before, performs at the same level in long run without compromising accuracy. And as you see, it's almost flat, the output of the LSTM. This merit makes it the most suitable model for long-term prediction. So we can say that LSTM outperforms all of other models in terms of long-term prediction. Recall the first research question: how accurately the number of bugs in a project can be predicted using time series analysis. We tried time series models including LSTM or long short-term memory, ARIMA, exponential smoothing or EXP, weighted moving average, and random forest regressor, with or without exogenous features for some of them. Surprisingly, the performance of a one-step prediction for all models is not significantly different. Furthermore, the baseline seems as good as others. The new finding, which was not considered in previous study, because in the previous studies they didn't have any baseline. For a second research question, we consider a 3 months prediction. For the Mozilla project, LSTM shows significant improvement compared to traditional time series model. The performance of the model is almost at the same quality as it was for a one-step prediction. And the concluding remarks. Time series analysis have twofold outcomes. First, to forecast the number of future defects that may occur in the system. Second, to identify the trends and abnormality in the system. The number of bugs reported to Bugzilla or Mozilla Firefox does not have a unit root, and therefore it is stationary. First, we checked whether it is a stationary or not, and we saw that it is a stationary. Furthermore, no specific trend has been observed in the dataset. It means that we don't have such a specific seasonality in the dataset that we have in some other time series prediction. Using a neural network, especially here, we use LSTM. We saw that it significantly improves the long-term prediction. LSTM is not affected by the residual error of the prediction when applied on the long-term test dataset, whereas other methods construct their prediction on the errors of the last period. Therefore, they are unable to challenge the robustness of LSTM that we saw in the previous slides. Using 8 different forecasting methods, we conclude that there are some improvement in the prediction performance compared to the baseline in general. Considering 5 different metrics, random forest with exogenous variables outperforms other methods. Nevertheless, we expect to observe a significantly better performance while all models have almost the same error distribution. It is all what observed in the method part or methodology part and the result section. For threats to validity, you may refer to the original paper for Canadian AI Conference 2020. This is the list of main references used in this presentation and also in the paper. Thank you so much for your time, and I really appreciate the time that you gave me to present my paper.